Hello. I'm going to be zooming in on a particular problem, which is looking at some data and making some synthetic data. So this is data from the Mimic Health data set that's already been mentioned. It's vital sign data. And something I want you to notice about this data is that it's about a single person. It's from the public sample. And this person has a temporal trajectory through the medical context they were in. So this exists in the Mimic data set alongside a bunch of other data specific to individuals. And I think it's an open question how we make a differentially private synthetic version of this data. The problem is that when we think about differentially private synthetic data, we often want to take some real data in a table and create some other data that's synthetic that also looks like that table. So an empirical distribution to an empirical distribution. But if we just do that with this data, we're ignoring the fact that some of these rows belong to the same subject. And of course, if we also ignore that fact, then we're actually not properly treating the privacy of these individuals. So there's two things, right? We want to maintain the trajectory through the medical context, and we want to respect privacy here. So each user owns an entire table. How do we create a synthetic data set that is a collection of such tables? One initial idea, I think it's very natural, is to flatten each user and change the column space accordingly. So we can sort of take each column, say heart rate, and instead of having one heart rate column, we have a heart rate column for time step 1, a heart rate column for time step 2, etc. That looks like this. Great, now we have one user is one row. Perfect. We can plug this directly into our favorite differentially private synthetic data method. You know, whatever you want. We've been talking about this for 2 days now, right? So there's lots of these. Maybe we're done. Those of you who have thought about this problem see some immediate issues, one of which is that we've now exploded the dimensionality, which is bad for these differentially private synthetic data methods. And the other is, of course, that we've now made the data artificially sparse. You know, some people will be in a hospital setting for a long time. Others will maybe have 1 or 2 check-ins. Those with fewer check-ins will have sparse data. So here's another solution, which I think is also very natural in the day and age of large language models, which is to serialize the tabular data as text. I'm not the first to propose this. You know, you can say sort of, here is my tabular data set where the value of column 1 is this and the value of column 2 is this, etc. So this is a format that's been proposed before. And if I do this with this medical data, it looks something like this. And then the question is, how do you fine-tune a large language model such that it will produce a structured table that represents somebody's medical trajectory? So we can start by, you know, creating examples in the serialized version for each individual in our data set. Can fine-tune some language model like Gemma with DPSGD, literally using prompts that look like this, like here are the first k rows, give me the k+1th row. We can do this process, and then generation, we can just prompt with an empty schema and generate row by row somebody's medical trajectory, but for a completely synthetic individual. Proper parsing here is very important. I think this whole approach is very natural, and you know, it's maybe not so surprising that the structure looks like this, but there's lots of details here that do matter. The other thing that we can do, which is a big trick these days in private text generation, is to overgenerate from a model that has, you know, differentially private weights and then do private selection, so we can do that too. And then we can output some structured data. So I think the hard part of this work is not whether we can generate such tables, but whether they're useful. What are the proper metrics? How do we examine this data? And I think this is hard in general because we have lots of different metrics when we were thinking about that table-to-table example, but this idea of a distribution over some collection of tables to some distribution over some other collection of tables is a much harder challenge, generally even outside of the privacy context. Here's a taste of the kinds of metrics we think about, which I think is cool. I do not have a background in time series analysis, so if you do, you've maybe seen this before. If you don't, maybe you also think it's cool. If we have two vectors of different lengths, and we know that they're ordered in some temporally relevant way, how do we measure the distance between them? Well, one idea is to materialize this matrix, where each cell here represents the distance from index I in vector 1 to index j in vector 2, and then we compute the optimal path through this, the optimal weighted path through this matrix. And that sum represents the distance between these two trajectories. I think it's a really nice idea, and we sort of generalize this over the whole collection of tables as one of our metrics. It also leads to this very nice visualization. We're kind of trying to figure out how to align these trajectories. It's not mine, somebody else's, but I think it's nice. So that's one of a few metrics we consider. Here are some of the other ones, and go to the paper for more details. But I think what's surprising is that you can do this process, and if you compare it to those sort of flattening approaches and then plugging directly into the black box models that we know work well for that table-to-table setting, this language model-based approach works really well. Produces data that we were surprised at how useful or how interesting it seemed from a temporal perspective. I want to note that we're still very far away from the real data, if we had access to that, but I view this as a step in the right direction, and this is with very small models, or small models these days, like Gemma 1b and Gemma 4b, for example, but you could imagine scaling this up and getting closer to performance that you might find actually useful in medical contexts. So in conclusion, it's hard. It's a hard problem. It's been a hard problem. I mean, this is we had this panel this morning for 20 years. It's been a hard problem. And it's a hard problem because of this flattening problem and other issues. But I think we're getting closer. Language models have a really strong prior over structured data and over temporal trajectories in structured data. And figuring out how to determine whether this is useful, we can do this process, but whether it's useful is, I think, also an open question. Thank you, and I don't know if I have time for questions, but thanks. Cheers.
Yeah, that was a good example of applying DP to a specific data synthesization problem for a specific type of data. So any questions from the audience? If not, oh, yeah.
Just want to quickly understand, how do you use this loss? Do you use it just for fine-tuning? Somehow how do you use the loss that you have defined over the sequences?
The loss?
Yeah, the distance. The distance measure, which I assume is then translates
the
to
distance measure that we actually, so we use standard cross-entropy loss when doing the fine-tuning. We don't, in private selection, we can use some of our sort of higher-order metrics, but that's a design choice based on what you want to use the data for.
I see. So use it for some private evolution or
Yes. Yes. Details in the paper on exactly that. Yeah.
All right. Thank you.
Thanks. Thanks, everyone.